Okay, in 7.1, we also have a model for the motion of a spring. Let's look at an example of a model from the physical sciences. We consider the motion of an object with mass m at the end of a vertical spring, as in figure 4. In section 6.6, we discussed Hooke's law, which says that if the spring is stretched or compressed x units from its natural length, then it exerts a force that is proportional to x, which is the restoring force, which is equal to negative kx, where k is a positive constant called the spring constant. If we ignore any external resisting forces due to air resistance or friction, then by Newton's second law, force equals mass times acceleration, then we would have the following. M times the second derivative of x with respect to the second derivative with respect to t is equal to negative kx. Now this is an example of what is called a second order differential equation because it involves second derivatives. So let's see what we can guess about the form of the solution directly from the equation. So if we divide both sides by m, then we have the following, which says that the second derivative of x is proportional to x but has the positive sign. We know two functions with this property, the sine and cosine functions. In fact, it turns out that all equations of equation 3 can be written as combinations of certain sine and cosine functions. This is not surprising. We expect the spring to oscillate about its equilibrium position, so it is natural to think that trigonometric functions are involved.